Hi, everybody. I'm Miss Lee. Today we're talking about rational applications. So rational applications is basically where we do some problems where they give you some information about distance or rate or time, and then you solve for the whatever is missing. So in order to do these kinds of problems, we need to know a couple of things. So one of the things that we want to know is that distance equals rate times time. I'm sure some of you have heard of this before. And so we're going to write out the meaning of each of these variables just to make sure in case you haven't. So E equals distance, R equals rate, and T equals time. And so just to rewrite this equation in a few different ways, you can solve for the R. And so you have R equals distance divided by time. So rate equals distance divided by time. You can kind of think of this as like speed. Speed is a type of rate where you have distance divided by time. So if you think about miles per hour, for example, miles is distance, and then per divided by hour, which is time. So R equals D over T. And then similarly, if you solve for time, that would be distance divided by rate. So T equals distance divided by rate. So in general, you want to use whichever one of these three that makes your problem more convenient to solve. And something that is good to know in general is that average speed is just total distance over total time. Okay, so if I ask you for the average speed, you want to find the total distance and then divide it by the total time. Okay. So let's go ahead and do a problem. The problem says Alicia rows a boat downstream for 182 miles. The return upstream took 12 hours longer. If the current flows at 3 miles per hour, how fast does Alicia row in still water? So you'll see that there's a lot of information in this problem, but the important part is that there's like this like upstream and downstream. So in general, when you're doing these types of river problems, when someone is going upstream, they're going to go slower because the rate of the current is going against them. So it would be, their rowing rate minus, and then whatever rate the current is pushing them at. And then similarly, if you're going downstream, you get the help of the current, and so the rate is increased by the current, and so you would add the rate of current to whatever the actual rowing rate would be. This works similarly with wind problems where you're being pushed by the wind versus going against the wind, where you would subtract the rate. So just kind of keep that in mind. So for these types of problems, I want you to always draw a table and kind of like organize your information. So we're always going to draw a distance, rate, and time table. And then you're going to draw one for this type of problem. You'll do one for going upstream and one for going downstream. Okay, so let's go ahead and fill in the information. Alicia rows a boat downstream for 182 miles. So what that means is the distance she went downstream is 182 miles. So downstream for 182 miles. We're going to go ahead and put that in the downstream distance. the return upstream took 12 hours longer. So we don't know how long the trip took, but we know that the return trip took 12 hours longer. So some amount of time for downstream. So let's just say T, and then upstream T plus 12. Okay, now it says if the current flows at 3 miles per hour, how fast does Alicia row in still water? So we're going to go ahead and say that the rate that Alicia rows in still water, we're going to call that R because that's what we want to solve for. We're going to call this R. And then we're going to give it a little subscript so we don't confuse it with anything else. So R sub A, and A is for Alicia. So if the current flows at 3 miles per hour, that would mean that when Alicia is going upstream, that's going to be making her go slower. So then you're going to subtract that from her rate. So it'll be R sub A minus 3. Now, when she's going downstream, that means that it's going to make her go faster. So you want to add that to the rate. So it'll be R sub A plus 3. Okay, so we see here we're missing some information here. We're missing, we have a blank here. So the question is, how do we fill that in? Well, let's just look. It says distance for upstream. Well, if you think about this problem, it's a trip going out and then a return trip. So it's going to be the exact same number. So the distance is going to be 182 for this one as well. Okay. And so now you want to try to write an equation out of this. So you want to write an equation out of this. And so for the upstream equation, you have distance equals rate times time. Distance equals rate times time. So that's 182 equals R sub A minus 3 times T plus 12. And then downstream, we have distance 182 equals R sub A plus 3 times time. Okay, and so you see here that you have two equations. We don't care about what T is since the question asks for how fast Alicia is rowing. So we're looking for R sub A. And so what you want to do is rewrite this so that you have these both in terms of T, and then we can set them equal to each other. Okay, so we'll go ahead and rewrite this. So upstream is going to be 182 divided by R sub A minus 3 equals T plus 12. And then we'll subtract the 12. So you have 182 divided by R sub A minus 3 minus 12 equals T. And then downstream, we have 182 divided by R sub A plus 3 equals T. So since both of these are equal to T, you can set them equal to each other. So just to go back real fast, what we did here was we solved for T. Okay, and so then now that we have a equation to solve, we're going to solve this the way we've learned. And hey, look, this is a rational equation. So we're now just going to solve this like it's a rational equation. So we're going to find a common denominator here. And so the common denominator would be r sub a minus 3. So we'll go ahead and multiply both the numerator and denominator, which would be 12 over 1, by r sub a minus 3. Okay, so over here, we'll distribute that 12, and so you have 182 minus all of 12 r sub a minus 36, because 12 times 3 is 36, all over r sub a minus 3. And then again, we'll distribute this minus sign and kind of simplify here. So when you distribute this minus sign, you have 182 minus 12 r sub a, so minus 12 r sub a, and then plus 36. So you're going to go ahead and do 182 plus 36, which is 218, over r sub a minus 3 equals 182 divided by r sub a plus 3. Okay, as you know, at this point you want to multiply both sides by the denominator. And so you have negative 12 r sub a plus 218 times r sub a plus 3 equals 182 times r sub a minus 3. Okay, so over on the left side here, we'll go ahead and make a box to make it easier. So you have negative 12 r sub a plus 218, and then r sub a plus 3. And we'll go ahead and multiply this out. So you have negative 12 r sub a squared, 218 r sub a, negative 36 r sub a, and then I believe 654. And then over here, we'll distribute this out. So ultimately, what you're going to end up with is negative 12 r sub a squared plus 182 r sub a plus 654 equals 182 r sub a minus 546. So what's convenient about this is the 182 r sub a minus the 182 r sub a will subtract to 0. Then we add the 546 to the 654. And we have negative 12 r sub a squared plus 1200 equals 0. And you factor out the greatest common factor, and you have negative 12 times r sub a squared minus 100 equals 0. And you'll notice that is a difference of squares. So we have negative 12 times r sub a plus 10 times r sub a minus 10 equals 0. And so you have r sub a equals negative 10 or r sub a equals positive 10. Well, let's reread the original problem. It says that Alicia is rowing a boat and we're trying to figure out how fast she would row in still water. Do you think she can row at a negative rate or go at a negative speed? Well, I don't think so. So we'll go ahead and just count the positive answer. And so we'll say Alicia rows uh, the boat at 10 miles per hour. And there you have it. That's how you solve an application problem with currents and winds and distance, rate, and time. Go ahead and try a practice problem and happy day.